In this example, we're going to pick up where we left off in the 2 degree of freedom system that we looked at earlier in this section, where we derived the state space model for it. And we're going to convert this into 2 transfer functions because we had in this system 2 observables, the 2 displacements, y and z. So we're going to get out 2 transfer functions in the end, y over u and z over u. So let's see where we left off with our state space model already done. So we have 4 state variables. We had y dot and y, we had z dot and z, although it was in the order of z dot, y dot, x1 through 4. And we derived it that way with our A matrix. Our B matrix was 4 by 1 since we had only 1 input in this system. 2 observables giving us 2 rows in C and 2 rows in D. And D was 2 by 1, the zeros matrix, because again, 1 input, so 1 column, 2 rows because we have 2 observables. So let's take this larger system and now let Matlab do the conversion for us to go from our state space model to transfer function form. I'm using here just some arbitrary values so we can do the conversion for the masses, the spring constants, and the damping coefficient. So I'll just enter those into our system. And I want to make our matrices as they were defined in the previous step. So our A, B, C, and D. And just check those out, make sure that they're going to be correct. A is 4 by 4 with the values, the rows and the columns in the same order that we derived our system. So with the same order of our state variables. B indeed is a column vector. C is 2 rows because I have 2 observables. D is a column vector, 2 rows for 2 observables, 1 column for 1 input. All right, so much like the previous one, let's start by looking at what do we get when we do this SS2TF. If I run just this, now, unlike the previous example, I have 1 input, so I have 1 row for A, again, A being the denominator of my both transfer functions in this example, and B is 2 rows, but each row is going to correspond to that particular row of, let's say, C and D, or really Y in that output equation. So here, the first row is corresponding to the first row for C and D. That was giving me my Z state, my Z variable. And then the second row is going to be the numerator for the transfer function that corresponds to the second row in my output equation. That was corresponding to Y. So the order I do my rows for C and D, or for my Y vector, are important so that I know that when I do this conversion, what row of the little b matrix corresponds to which transfer function. So now I can make both of my transfer functions. So what I'm going to do here is I'm taking just the first row, but all columns of B, and making what I'll call cis Z. This is my Z over U. That's the first transfer function. So just this first row of B, and then they're both transfer functions are going to use that same denominator. So we can carry through with that. Then my second transfer function, y over u, where I'm calling cis y, is using the second row of B. So the second row of B, and again, that same denominator. So let's see what those look like. Now, this is less obvious if it's right or not, because it's not just that simple spring mass damper like we saw in the previous example, but we can just do some checking here. So this is my z over u, so I get 2s plus 10 over s to the 4th plus 22s cubed plus 140s cubed plus 60s plus 300, and that indeed does correspond to, well, see for a, my denominator 1, 22, 140, 60, 300, and it wants my leading coefficient to always be 1 when it does this conversion. And looking at the B, again, 2 rows. So the bottom one, we should have 10, 2s, and 1 times 2s squared, or 1 times s squared. And that's what we get for the y one. And for the other one, we have 10 and 2s. And indeed, we have 10 and 2s for the z over u. All right, so that's good news. So we have these 2 transfer functions now, 1 for each output, based on that same input. So the conversion looks like it was done right. We can do a little bit of checking. Let's look at this A matrix, 4 by 4. When I take its eigenvalues, I will have as many eigenvalues as I have the dimension of A. So 4 is what I should expect. So if I do my eigenvalues, I get 4 eigenvalues. And for this particular setup of parameters, I get 2 complex conjugate pairs. They are both in the left half plane. They both have negative real parts. And again, they're complex conjugate pairs. We have negative 10.95 plus or minus 3.98j, or I as it's represented here. And then the other pair, negative 0.043 plus or minus 1.49 about I, or j. Right, so that's nothing too special at the moment. It does tell us about the stability. But let's look at my denominator and see what the roots of it are. That is to say, what are the poles of, in fact, both of these transfer functions. So what's the poles of this denominator? We should have 4 poles because it's 4th order. And let's see what we get. And compare that to the eigenvalues. And as we should expect now, they match each other. The poles of the transfer function are the same as the eigenvalues of the A matrix. And finally, let's look at going in the reverse direction. I want to take my B as a matrix, so 2 rows to it, and my A as a row vector, and go back and get A, B, C, and D matrices. Keeping in mind that's not going to look exactly the same as how we started, because it might shuffle around the state variables that we're using. So it might interplay some of the rows and columns that we had in our original system. So let's see what we get though. So D, well, that looks the same, it's just zeros, so it might have swapped rows, we can't really tell. But actually the C matrix is pretty different than what we had. The order is different, the columns are different, potentially the rows are different, and it's not just ones and zeros. The B matrix, it looks like now the bottom row is on the top. And our A matrix, I'm calling it A1 here, so it's different. Let's compare that to the A matrix we had before. Definitely looks different. The rows are switched, the columns are switched. The state space model it came up with is a correct state space model, but just keep in mind it's going to be represented a little bit differently than how we derived it initially. It swapped the order of our state variables, and we just have to make sure that we can interpret this correctly. So again, our C matrix looks very different, but should be giving us the same results. And the A matrix we got also is looking different, but we should be getting the same results out of that as well. So like we saw in the first example, that TF2SS doesn't work out quite as nicely if we start with the transfer function and then get a version of the state space form. But going forward, state space 2 transfer function, that does a pretty good job, at least in this automated way.